Okay, so I'm gonna lecture instead of, well, there is no video for looking at OrthoPara and MetaPara Directors. So I'm going to lecture on that, and then at the end there may be some time for questions. Otherwise, you can email me your questions or questions for Wednesday before the exam.
Wait, this is the exam material you're about to introduce just for now?
Am I going to introduce exam material? I don't know yet. So we'll wait and see after I'm done. Okay. And I know it's spring break starts Friday after the last classes, but the university apparently has scheduled some events for people to leave, or you've scheduled. I need to know about those today. So if you have some university event you're going to be on, you're not going to be here Friday, you need to schedule to do the exam this week before you leave. And if you're in lab, I need to know that you're going to do a makeup lab, preferably in Dr. Dowd's section tomorrow, or we make arrangements. Okay, because I don't want to go into finals week. Oh, you're not here, you didn't talk to me. Because then you know what happens, then it's a 0. So, it's not make your own spring break week. Okay, I mean, I hate to say that, but it's gotten to that point where everybody just decides when they're going to start their spring break. After the last class on Friday is the official answer. Okay. So, we know the groups that add to benzene, that when we add them are activating and which ones are deactivating. So, at some point we're going to need to put together a list where we have an N group, an O group, an R group, another benzene ring group, an R group. Those 4 groups all cause the benzene ring to react faster. And so those are all activating. On the other side, we've got halogens, we've got carbonyls, we've got nitros. Now let's see, we've got C triple bond N in between. We've got nitro, and then we've got ammonium where there's an N plus. Okay, so those are the deactivating groups. They all cause the benzene ring to react slower. And this table that's in the PowerPoint notes goes from the most activating down to the most deactivating. And an H would be number 5, because that's a benzene ring. So everything above hydrogen reacts faster, everything below hydrogen reacts slower. So if I take a look at my activating groups, one of the things I can do is I can say, well, the generic form of an activating group is an atom with a lone pair attached to it, like oxygen and nitrogen. Now, the benzene ring and the R group we'll have to deal with. If I look at a deactivating group outside of the halogens, the generic form of a deactivating group is to have an X double bond Y group where X is slightly positive and Y is slightly negative. Right, that'd be a C double bond O, It would be a C triple bond N. It would be even an NO2 because it's N double bond O with a single bond to the O. Because there's the structure of a nitro group. So what I'm going to do is I'm going to use these activating groups to model most of the molecules that are on this table. Now, when I take a benzene ring that already has a group on it, and I react it with an electrophile, there is a regioselectivity that needs to be dealt with. So, is the electrophile going to add to the ortho position, to the meta position, or to the para position? Is there a system to this? Is it just random? What's the regioselectivity? And it would be really nice if there was no system. If this was just random, we'd say it's just random and move on, but it's not. It depends on what Y is. So if Y is activating, so if you put an activating group on the ring, you add the electrophile to it, what people have found is that they get a mixture of ortho and para products. And what I mean by that is that they get virtually no meta product. What? Activating. For the activating group. So we don't get any meta product when we use an activating group. So then what this activating group is called is an OrthoPara Director. Okay. And the critical part of the OrthoPara Director is that the activating group tells the electrophile where to add. You're going to add ortho and para to me, the activating group. Okay. But no meta. So then when you do the reaction where you take a deactivating group and you attach it to the ring, guess what you get? You get meta. And you get the meta almost exclusively. You get very little ortho and very little para. Okay. So that deactivating groups then are called meta directors. So there has to be a reason why. There has to be a reason why we get OrthoPara as activating groups do OrthoPara direction and deactivating groups do meta direction.
So with deactivating, will it be pretty much 50-50?
Not necessarily. It depends. Sometimes with the activating group, if it's a large activating group or if it's a large electrophile, it might add only para. But we'll get to that in the next 2 weeks, like after break. We'll talk more about that. Brian?
But for the same exam, if you ask for like the major products, we would consider them equal?
You put both down.
Okay.
Anytime I give you that as a problem, you're going to put both down. Going from there, you can select whichever one you want to use, but you put them both down. Right. So activating or OrthoPara directors deactivating or meta groups or meta directors. So we have to deal with the issue of why. Why do OrthoPara directors direct OrthoPara, and why do the deactivating groups do opposite? So I have in the PowerPoint, I've got all of the intermediate carbocations, but I figured I might as well do this from scratch, because then you'll write it down and it'll maybe sink into your head a little bit easier if you're writing it, as opposed to I know what happens when I put the PowerPoints up on the board. Everybody just kind of looks at and does other stuff. So I'm going to start with a general form of an activated group. So an X with a lone pair. That could be oxygen, it could be nitrogen, probably even could be a sulfur. And now I'm going to add my electrophile to each position. So if I say, okay, I'm going to go ahead and add the electrophile to the ortho position. If I do that, I'm going to get that as my starting. That's going to be my starting carbocation. I'm going to go ahead and do it for meta too. So if I add my electrophile to my meta position, it's going to put the plus charge there. So again, I'm doing the first step in like any electrophilic addition. And then in terms of my para position, I will do the same thing by putting an H, an electrophile, and that's going to put a plus charge there. Nope. Nope, it's going to put a plus charge there. Okay, so there are my initial carbocations from adding the electrophile ortho, meta, and para. Now, what I need to do is I need to write the resonance structures, all the possible resonance structures of each of these intermediates. And the one with the most resonance structures is going to give me the major product of the reaction. So this is like 1, 2, 1, 4, 1, 6. I'm going to take this pair of electrons, move it here, so that I can put the plus charge here. Just to be more efficient, I'm just going to go ahead and put in my I'm going to make my benzene rings with my X groups on it. You can do the same thing, because there's going to be 3 for each one. So then for the ortho, move this pair of electrons over. That puts the plus charge there, and it puts the H and the E. And I should probably have done that too. So if I put in all the X's, all the E's and H's, now all I got to do is just put in my double bonds in my chart. Okay. So now Third ortho, move this pair of electrons here. That puts the double bond here, and the plus charge there. Okay, so there are the first three resonance structures for ortho addition. And there's nothing spectacular about that. So let's do that down here. Let's take this pair of electrons, move it here. So now the double bond goes here, here, with the plus charge there. And then if I move this pair of electrons here, that moves the plus charge there. Now, stop for a minute. Looking at the ortho and the meta positions, look at the positions of the plus charges around the ring. Are they the same? Are they in the same positions as when I started by adding the ortho position? Okay, you got a marker of the X as in the same place. Do the plus charges, are there any structures in the ortho and meta where the plus charge is on the same carbon relative to the X group? No. So the 3 for ortho are different than the 3 for meta. Okay. Everybody see that? So now let's do the para. So again, I can take my para and I can move my lone pairs around. Flush. Now, looking at the para positions of the positive charges, they're like the what? Those plus charges are in the same position as when I added ortho. Okay. So first things, whenever I add a group to the ortho or the para positions, the plus charges go in the same carbons, go on the same carbons in the ring. Right. Now remember, I've got OrthoPara Directors and Meta Directors. So that simple fact groups OrthoPara together and leaves Meta out. The fact that the plus charges all go in the same position in ortho or para, and they go in a different position with meta. So that sets how the groups are going to be grouped together. Ortho going with para. Lisa?
Can't you just say, like, based on the X attached, whether you could just go clockwise or counterclockwise, like based on like whether it's weak, strong, now?
To explain whether it's ortho, to explain why an activating group is ortho or para, we need to write all the resonance structures and determine which of these intermediates has the most resonance structures. In other words, which intermediate is the most stable.
Okay, and the one with the most resonance will give what?
Will be the most stable intermediate. And the most stable intermediate is going to give the major product. So that's our goal here. That's how we're going to tell. Somebody said, "Hey, show me why ortho and para are formed from an activating group." That's what I'm doing now. And I've got to write at least 9 resonance structures to answer that question. So that's my goal. Except right now, what's the situation? They're all the same. I got 3 for each. Or do I? What if I take the original structure here and take this lone pair and share it with the plus charge, so that I form a 4th resonance structure? So if I share the pair of electrons off of the group that's attached, what do I have? I now have a 4th resonance structure. And because ortho and para do the same thing, I could take this resonance structure, right? And I could share the pair of electrons this way, and that would give me a 4th resonance structure for the para addition. So now ortho and para are in the lead. They've each got 4 resonance structures. Now, can I do that with the meta? Why not? Why can't I do that with meta? Because the positive charge never is next to the X group. Right? I'm waiting for confirmation from others. Okay. So now what do I have? I've got 4 resonance structures, 3 resonance structures, 4 resonance structures. Which additions form the most stable intermediates? Ortho and so an activating group with an X with lone pairs, the most stable intermediate is when it adds ortho or para. And that makes oxygen, nitrogen, any atom with a lone pair that's attached to the ring will direct ortho and para. May?
The electrons on the 4th structure for para, are they supposed to remain?
No. No. That's why it's got a positive charge. So that's what I need to do to show that the activating group is an OrthoPara director, because its intermediates, when you add ortho and para to it, are the most stable. Josh?
Now, as we stated earlier, there's so the benzene ring and H is kind of special in the activating group.
So now I've got to deal with these two, right? So now I've got to explain why those are the case. And then I've got to go to the other side and I've got to explain why all the deactivating groups are meta directors. Yeah. We'll do that. We're going to try and avoid writing like all 9 resonance structures. Betty?
I'm confused with X. Like you're adding a halogen with that.
No. X is any, well, yeah. X is any group with a lone pair, and actually it could be a halogen. X is any lone pair, and it could be a halogen. Because what I guess I didn't tell you, I forgot to tell you was that all of these guys are OrthoPara directors, not the hydrogen, but and all of these guys are meta directors, and the halogen is deactivating, but it's OrthoPara directing. So of this, the halogens are the exception. Halogens are deactivating, but they're OrthoPara directors. And normally I'd wait till the end and say that, but I might as well, since you brought it up, I might as well say that now. That because the halogens have lone pairs, when they direct, they behave like a nitrogen with a lone pair or an oxygen with a lone pair. So halogens, OrthoPara direct, because they've got the lone pair, and because that lone pair then makes ortho and para intermediates have more resonance structures, which makes them more stable. And the more stable intermediate gives you the major product in electrophilic aromatic substitution.
Go back to 5 for 2 seconds.
So halogens can double bond?
She said 2 seconds. Did you get it?
So halogens can double bond?
Yep. Yeah.
I've never seen that.
You've never, well, I mean, a halogen here could have a double bond with a plus charge. It's not very stable. Nobody's saying that this resonance structure right here is very stable, but it exists. Right? And none of these resonance structures are a true intermediate, are they? Because the true intermediate is the resonance hybrid. So that additional fourth structure, even though it's not very stable, causes that whole resonance hybrid to be more stable than the middle one. And that's enough to tip the scales towards activating groups with oxygen and nitrogen and a deactivating group with a halogen. They all direct ortho and para because they form the most stable intermediates. What I'm doing is I'm saying anything that looks like that is an activate, well, no, I can't say it's activating, but I can say it's an OrthoPara director.
What was the significance again of having the most resonance structure? I understand that the most stable intermediate is the major product.
The most stable intermediate is the one with the most resonance structures. Whenever you can write more resonance structures, you become more stable. Okay. So really, this is about forming the most stable intermediate. That will give you the major product.
That X with the lone pair.
Yep.
That's one of those separate activating groups.
That represents a nitrogen, or it could represent an oxygen, or it could represent a halogen. So when that situation exists, that group's going to direct OrthoPara.
That's because everyone.
That's because it has a lone pair to be able to donate.
What's the benzene R group?
I'm going to get to them. Because they don't have lone pairs, right? So if they don't have lone pairs, I've got to basically redraw this entire chart with all 9 resonance structures. Yeah, right. People, no, don't do that. Well, I wouldn't. I would just erase groups on my thing. I would just erase the groups to make it new. But that's cheating. So let's deal with the ring first. So, are we all in agreement that the key structures for the activating group to be OrthoPara is when the plus charge is next to the substituent? Because if the plus charge is next to the substituent and I can draw additional resonance structures, that makes it OrthoPara. Okay, if we're all in agreement of that, then if I've added my electrophile to the ortho position or the para position, and I get the plus charge next to the benzene ring, how does the benzene ring either stabilize that plus charge or allow me to draw more resonance structures? I can take this double bond now. I can move it here. And there's my fourth resonance structure. Right? So one of the double bonds from the ring can now be used to form an additional resonance structure. And in this case, how many more resonance structures could I draw? I could draw 2 more if I delocalize the positive charge in that second ring. So why does another benzene ring activate the original benzene ring? Well, why is it OrthoPara Director? Because when the plus charge is next to the ring, it forms additional resonance structures. That means when I add my electrophile ortho and para, I get more than 3 resonance structures. Because I know when I add it meta, I get 3. Okay, so when the positive charge is next to a ring, same thing happens. I get more stable, I get more resonance structures, more stable intermediate, OrthoPara Director.
There's even more than 4 resonance structures. Why is it less activating than the other ones that we just looked at?
Well, that's a good question. What's the other benzene ring giving up to form those additional 3 resonance structures? It's giving up its own aromaticity. So again, we're not talking about these being very stable, but that's a big sacrifice. So yes, it activates, but not by very much. See, the nitrogen with a plus charge, it can handle it. But to break up the aromaticity on the second benzene ring, that's a pretty big sacrifice. So that's why it's like 3rd on the list. And remember, these are all based on reaction rates. So, as I kind of said last week when we were talking about the benzylic carbocation versus a tertiary carbocation, when you're dealing with energies, all of the rate equations and stuff, the Arrhenius equation, they're all logarithmic. So you get big effects with small changes because it's logarithmic. Or it takes big changes to create small effects, depending on whether it's an e to the minus or an e to the positive. So it still increases the rate, but not as much as a nitrogen or an oxygen. So when I put an oxygen or a nitrogen, it increases the rate, and it still does go OrthoPara. All we're doing today is we're justifying activating groups being OrthoPara Directors by forming additional resonance structures, more stable intermediates, which then cause that to be the major product. Right. I usually would say, everybody okay with that? But I was reading something this morning where that's like, I should never ask that question. I shouldn't ask vague questions like that. We should take a couple minutes and you should write a little short essay on what you're getting and what you're not getting. But is everybody okay with that? Because the short essay thing is... Sarah?
So I don't want to like presume the wrong thing, but is it everything above the H is OrthoPara Director included, and then also X, and then H and everything below the X would be Meta Directors?
No, H is just H is a benzene ring.
Okay.
There's no direction. If you have 6 H's on your ring, there's no ortho or para.
Okay.
So H is benzene. H is the baseline. So this is benzene. Everything above benzene is activating.
Okay.
Everything below benzene, which means that it's over here on the other column,
Okay.
is deactivating.
Okay. And then X.
And halogens are deactivating, but they're OrthoPara Directors. Now, what about the R group? Now, let's imagine in these 9 that we wrote. What happens when there's an R group next to the carbocation? What kind of carbocation do I form if there's an R group here? Tertiary. So R doesn't give us the 4th resonance structure. But what it does give us is a tertiary carbocation and 2 secondaries. What do we get when we add to methyl if those were R groups? If each one of those X was an R group, how many secondary carbocations do I have? 3. So I don't have a tertiary. Now when I go to para, what do I have? A tertiary and 2 secondaries. So when you put an R group on the ring and you add ortho or para, you end up with a tertiary carbocation and 2 secondaries. When you add meta, you end up with 3 secondaries. So what have I done overall? Because I've got a tertiary and 2 secondaries, ortho, para, those intermediates are a little bit more stable than 3 secondaries. Lisa?
I was going to ask you to come up with problems in our group.
Here's what I would do for the R's, if I could. I would have erased everything here, and I would have just said, I'm going to put my R group there. And I would have erased everything else. This isn't, right now we're not doing problems. What we're doing is we're justifying why the R groups are OrthoPara Directors. Okay. If I was to put this on the test, I would give you a molecule and say, write all the resonance structures for ortho, meta, and para direction. And you would do this. And then tell me whether the group was ortho or para or meta directing. That would be a huge mechanism problem, right? Because you've got 9+ resonance structures to draw. So the key word there was if, right? And the big question is, if I wanted to grade all that, but remember, I have all of spring break. Right? But this is what we're doing. We're justifying why each one of these groups is what it is. So the X with the lone pair, that got rid of 3 groups for me. That explained 3 groups on the chart. We just did the benzene ring. That explained another one. And then the R group explains the rest of the activating groups. Okay. Right. We okay so far? So that means I have all those Sarah.
Sorry. I just want to double check I got it. So you said ortho and para get 1 tertiary and 2 secondary?
So if these were R groups, if these were R groups, you'd have a tertiary, a secondary, and a secondary.
So you don't count 4?
There is no fourth.
Oh, that's only...
Because if there's an R group here, there's no fourth resonance structure.
Oh, because there's no lone pair.
Right.
Okay.
There's no lone pair, there's no double bond. Okay. So now, I've got all these deactivating groups to do. Well, actually no. Because we've already taken care of halogens, right? So let's go back and let's just draw the key intermediate for if there's a deactivating group on the ring. So I'll add my H and my E if it's ortho, or if it's para addition. I end up with a plus charge next to the group. Now, all the deactivating groups except halogens can be summarized by this group, X double bond Y, as a generic structure. INO C triple bond N is one of them, but it's the same formula, right? You've got an X multiply bonded to the Y. And in that, the X group is delta positive and the Y group is delta negative. Right? In all of those molecules. And let's go back here. So C double bond O, C triple bond N, NO2, which is an N double bond O with an O minus, but the more important thing is that N is a positive charge, a full-blown positive charge. And then we've got another N with a full-blown positive charge if I add 4 alkyl groups to a nitrogen. So X double bond Y has a slightly positive charge, and then the nitro and the N plus have full-blown positive charges there. Okay, so now let's go back and take a look at that. I haven't gotten to the, I do 3 resonance structures for each one, for ortho, meta, and para direction. But these are the critical ones for ortho and para, right? Are they stable? Are those resonance structures stable? If I said they were unstable, what would make them unstable? If I said as a fact, those are unstable. What? The positive charge. That's the critical part.
That's by the thermal cation.
Well, it's, what are we talking? You're talking about the full-blown positive charge, or are you talking about the delta positive charge?
I'm talking about the full.
The full-blown one. What's it next to? A delta positive, right? Or in the case of nitro and the N with the 4 groups, it's next to another full-blown positive charge. Are those stable situations? No. So, when the positive charge was next to certain groups, when those groups were activating, they stabilized all the resonance structures. They stabilized the intermediate. But now I've got a set of groups where they're doing what to that resonance structure? They're destabilizing it. So the deactivating groups now, whenever they are next to a positive charge, they end up destabilizing this to the point where I could say, you know what? That third resonance structure, it's not valid. So in my PowerPoint notes, you'll see I did this. So I have 3 for each addition, and then for ortho and para, I've got a big circle drawn through it. Because that resonance structure was the key to being more stable for activating, but when you put a deactivating group on, what happens? It destabilizes it. So now I basically have for ortho and para, I've got 2 resonance structures of the intermediate. What did the deactivating group do to the meta addition? What would the deactivating group do? Did nothing. Why? Because the carbocation is never next to the group. So that still, all 3 of those resonance structures are legit. But when the plus charge gets next to a deactivating group, that resonance structure isn't stable. So now I've got 2 resonance structures for ortho, 2 for para, and 3 for meta. What's the more stable intermediate? Meta. And so what do the deactivating groups do? Direct meta. So it's not like meta's kind of, I don't know, it's not even really favoring the deactivating groups really aren't favoring meta. It's just that they're killing the ortho and the para. But all of these boil down to one thing, and that's what about when the positive charge is next to the group? If that group stabilizes it, it's going to be activating. If that group destabilizes, it's going to be meta directing. So that's how we justify our chart in terms of ortho, para, and meta directors. The oddball ones are halogens, because while they deactivate, they've got lone pairs, and so they act as activating or OrthoPara Directors. And the thing is, that's a fact. All the reactions, you do all the electrophilic reactions, you look at all the products, and you come up with this chart of ortho and para directors. You take and measure the rates of the reaction, and you rank them from 1 to 10. So whether it's activating or deactivating, whether it's OrthoPara or meta director, those are facts. What we're now trying to do is to justify or provide a reason for those facts. Okay? There's nothing here that's too much out of line. But we're talking sometimes about small energies. Okay. Now, with those groups, we can talk about specific molecules. So we can say, is this one, if I add my E+, where's it going to go? The E plus in this case is going to go meta.
Yeah.
The E plus in that molecule is going to go
Does it matter? Like,
Yeah.
besides- I mean, I know it matters. I'm saying, like, if, I know it's based on the first one, but
Oh, wait, no, meta,
it was, it,
meta. I think it's that.
yeah, I think.
Because the O has
No, we could. Oh, with the double bond with the O, would it have a positive charge? Because if it has a positive charge, it has a piece.
Anybody else want to weigh in?
Wait,
Because he's confused. He's given both answers.
or nothing will happen.
No, something will happen.
Okay, well.
How many people say that the electrophile here is going to add OrthoPara? How many say it's going to add meta? Yeah, I'm not accounting for all of the hands. Okay. Well, the first one was meta because the carbonyl was attached to the ring. What happens when I reverse it and I put the O next to the ring? It's now an X with lone pairs, and so that oxygen is now going to act as an OrthoPara Director. That ring is activated. This group on the right is activated. The group on the left is deactivated. This one's going to be meta, and this one's going to be OrthoPara. So we need to be careful as to what group is directly attached to the ring. And then the other question that I can ask, which will be the last one, would be I can now think about giving you groups that are not on the chart. So I could give you, for instance, a sulfonic acid and say, where is the sulfonic acid going to direct the electrophile? Is it going to direct OrthoPara? Is it going to direct meta? Why? Because you've got an X double bonded to a Y group. So those generic molecules that I used in the mechanisms, those are helpful because they can help me in these situations where I don't necessarily know what the group is. But if the group fits to one of those models of X with a lone pair or X double bond Y, I can classify it. Okay. All right. So this is how we justify groups being ortho, para, or meta directors. Okay. Now, what are you going to have to know for Friday's test? You're just going to have to know whether they're activating or deactivating. Okay? Because we need to do a little more work in terms of now actually adding the electrophile to these molecules and getting the OrthoPara products. Because then the next thing I'm going to say is that the next thing that comes after that is I've got two groups on the ring. Where does the electrophile go? Which is really easy if you know this chart, and there's better chart in the PowerPoint notes, but you're going to have to know that chart from number 1 all the way down to number 10 in order to answer that question. Okay, and that won't be for Friday, that'll be beyond Friday. Okay, so the exam material stops at which groups are activating, which groups are deactivating. Right. So here's all of your homework assignments, graded and stapled, so you can take them, and then you can turn in the problems for today. I'll try and get them graded by next week. or not, or by Wednesday.
I had a question about that one that you were just talking about, the
Activating, deactivating, how they add.
Yeah.